Yeah, it started.
Oh, it is started. Hi, everybody. I'm Merdad. I'm a postdoc at MIT. Today, we are going to present with all the authors of our paper, except Yun Tetley and David Woodruff, our new upper and lower bounds for the bit complexity of communication for a bunch of different fundamental convex optimization problems.
Hi, everyone. I'm Swati. I'm also a postdoc at MIT.
William, I'm a postdoc at CMU.
Hi everyone, I'm Guang Hao. I'm a PhD student at MIT.
So without further ado, let's get into the definition of the problems and our results. So we are going to talk about distributed optimization. So we are assuming our data is scattered on multiple machines, and there are like several machines. We show the number of them with S, and we index the machines with numbers 1 to S. We assume like some structure about like how the data is partitioned over the machines. For example, it is not like random entries of the machine, random entries of the data are put on different machines. Here, we are working with like linear algebraic problems. So we assume like we have a vector, we have like a matrix, and the rows of the matrix are partitioned to different machines, and the corresponding entries on the vectors are also on those, machines. So this is like the structure I'm talking about like how the data is partitioned. And it makes sense because like, for example, you can think of like the data of like a bunch of different patients in different hospitals is scattered over like the machines in those hospitals. And our goal is to find like the minimum amount of information that is needed to be communicated between the machines so we can compute a solution to a optimization problem, for example, linear regression of the form that you see on this slide.
And there are two main models of communication. The first one is what we call coordinator model, which is also called as point-to-point model. In this model, any communication between machines has a cost. It means that communicating a bit of information to all machines costs S times the amount of information. Here, S is number of machines. And there is another model of communication which we call as blackboard model, which means writing on the blackboard has a cost, but reading from it is free. So communicating a bit of information to all machines only costs you 1. And there are many works consider rounds of communication or number of communicated words or numbers. Although this might make sense for the more combinatorial or graph problems. For linear algebraic problems, they do not provide accurate bounds due to the stability issues. In this work, we consider the number of communication bits. This is pioneered by the work of Wempler, Wang, and Woodruff in SODA 2020.
So we consider several different problems from convex optimization in our paper. The first one is linear regression and LP regression for general P, where, as Medha described, all the matrices and vectors are partitioned on different machines according to the row partition model. We study this problem under the coordinator model of communication. We also study linear programming, again with all the data partitioned according to the row partition model, again in the coordinator model. And finally, we study the problem of finite sum minimization of FIs, where each FI is convex, potentially non-smooth, and supported only on a few coordinates of the problem variable. Throughout our paper, we use D as the parameter for dimension, S for the number of machines, and L for the number of bits of input numbers.
So first, let's start talking about like regression and low rank approximation. Our first result is like for probably one of the most fundamental problems in optimization, which is linear regression. Wempler, Wang, and Woodruff gave a bound of SD squared L for solving this, which is essentially just doing it using normal equations in a distributed way. This is also a typo. This is like STOC24. It's not 2019. We here give like two bounds that are with high probability. So there is like a small chance of like failure, but it is like polynomially small. But we solve it like faster than the bound of Wempala-Wang-Woodruff. Our first result give like a low accuracy solution. And the other caveat of it is also that the solution is only available on the coordinator. So the coordinator is like, it could be any of the machines, but like we pick one of the machines as the coordinator and all the machines just talk to that machine. Like if they want to communicate some bits between each other, they first send it to the coordinator and the coordinator send it to the other machine. So our first result gives like a multiplicative factor error, like a 1 plus epsilon times the optimal error. And it uses SDL plus D squared L times epsilon to the -1 as the communication. So probably like the advantage of this model is that there is no dependence on the condition number of the matrix. The second result has a dependence on the condition number, but the good thing about it is that it gives a high accuracy solution. And the second advantage is that the solution is available on all the machines. As we will see later, we need both of these properties for our linear programming algorithm. And this gives like SD times L plus log kappa times log of 1 over epsilon instead of 1 over epsilon itself plus D squared L bits of communication. Both results are based on first finding a spectral approximation of A transpose A, and then the second result uses an iterative approach that I'll explain a little bit in the next slide to find like a high accuracy solution using preconditioning. So our iterative algorithm is based on Richardson iteration, which is like the formula you see. Previous work has shown that this works like with bounded precision. Like if I use numbers with log kappa over epsilon bits, this Richardson type iteration still converges. Here we make an improvement. What we do is that we show that we only need to look at like middle bits for our points. By middle bits, I mean like the bits that are not like have too high place value and not too low place value, and only perform the iterations on those. And that actually improves like a log of 1 over epsilon factor in our bounds. So essentially, we are improving log of 1 over epsilon squared to log of 1 over epsilon. For the details, you probably need to look at the paper to see like how just using the middle bits work. And just to summarize, like other results other than like linear regression in this part, we have like results for p-norm regression for p between 1 and 2. With complexity of SDL plus D squared L to the epsilon -4. That exponent of epsilon with like -4 is probably not optimal. So if people are interested, they can work on that. And this is based on like a recursive Lewis weight sampling approach of Cohen and Peng. And last results in this part is that we find a low rank approximation to the matrix A as like a B by K matrix pi, which is only available on the coordinator. And we use like KL times the epsilon to the -2 plus S times epsilon to the -1 bits of communication for that. And it gives like a multiplicative 1 plus epsilon approximation in Frobenius norm.
In this section, we consider about solving a linear program in coordinator model. Here again, we consider the row partition model. That is, each machine holds a part of rows of constraint matrix A and cost vector C. For this problem, our algorithm gives a total communication complexity of roughly SDS times d to the 1.5 times L plus d squared many bits. Here the kappa is condition number of the constraint matrix, and R is the LP's inner radius. There exists a favorable point X with a ball L2 ball at least a radius R, and the big R is outer radius of linear program. There is all the favorable solution have L2 norm less than R. And L is the length of word of input numbers. Moreover, at the end of algorithm, the solution vector is available on all the machine set. And our algorithm is mainly based on the least for barrier interior point method, which runs for square root d times log 1 over epsilon many iterations. And in each of iteration, we require solving a linear regression problem of the form that minimize x in WAX minus WB. Here, W is a diagonal matrix which only depends on the current solution and the current stack to the high accuracy. We maintain a spectral approximation of A transpose W square A with SDL with roughly SDL plus D square many bits of communication using our linear regression primitives. And using those spectral approximation as preconditioner, we utilize our high accuracy regression algorithm to solve the regression problem in each iteration. At the beginning of the algorithm, we need to find a favorable point. To find that favorable point and the slack, we need to solve a Lewis-Waite problem. So which again we use the fixed point iteration scheme given by Cohen and Pong.
Okay, so we now consider solving this finite sum minimization problem. In contrast to the previous problems that we solved in the coordinator model, we are solving this in the Blackboard setting. Here, each Fi is convex and Lipschitz, meaning it could be potentially non-smooth, and it's supported only on di out of d coordinates of the problem variable. And the ith function can be accessed by the ith machine via zeroth and first order oracles. So the finite sum minimization problem captures important problems in machine learning, like empirical risk minimization. But the additional structure of being supported on only di coordinates appears in important applications like decomposable submodular function minimization. So our main result in this paper is as shown here on the screen, meaning we get an epsilon accurate solution in number of bits given by summation of di square, where I'm not saying the log factors. And at the end of our algorithm, all servers hold this minimizing vector. So this result improves upon the result obtained by using classical cutting plane method, as well as the one by Dong, Jiang, Li, myself, and Guanghao in our NeurIPS paper. I also want to mention that if we try to use any variant of gradient descent on this problem, that's going to incur a very high, it's going to perform very poorly when the condition numbers of the functions, FIs, are large. And it requires, more particularly, it requires a bounded condition number on Fi. So our main approach in this is to combine interior point methods and cutting plane methods to adaptively choose the right function Fi to optimize in any given iteration. So as a first step, we do this standard epigraph trick and transform the problem into the one shown on the screen. In particular, the KIs here, they have decoupled supports, and the structure of the FIs, which we originally had, is now captured inside the linear system AX equal to B. And the sets KIs are all disjoint. So, and also the first order oracle for the functions fi transform into separation oracles for the sets ki. So in each iteration, we move the current iterate towards the centroid x star out of k out, where the centroid is defined using the entropic barrier. And we do this update only if we have feasibility of x star out. And we do this update using the interior point method. If, on the other hand, x star out is not feasible, then we use the output of the separation oracle to update the set, either by pruning the k out or the k in. And in doing so, we always ensure that we choose the correct set ki. And so this addresses the central weakness of all other approaches for this problem, which do not choose FIs adaptively.
So finally, I'll say something about our lower bounds for linear regression. So our upper bound for linear regression had an SDL dependence. For getting constant factor approximation, we used SDL plus D squared L bits. So the D squared L part of the lower bound was already known by Vimpala, Woodruff, and Wang. So the interesting question is whether SDL is optimal here. So SDL came from each of the S servers sending D coordinates to the coordinator, and each of those coordinates was L bits, so that gave an SDL dependence. So you can ask whether this can be improved by doing some sort of rounding, for example. So maybe you don't need to send all L bits of each coordinate to the coordinator. But we show that SDL actually is necessary, at least for protocols that use a somewhat restricted number of rounds, so at most L over log L, and without any assumptions on the condition number of the system. The system is well conditioned, you could hope to do a little bit better. So to prove this lower bound, we need a new communication primitive that lets us get the bit complexity lower bound. So that's the L dependence. And this is because the usual lower bounds are sort of combinatorial and don't give us a good way to get a bit complexity lower bound. So we introduce a new communication primitive here. So the problem is that Alice and Bob hold unit vectors B and W and RD. And by communicating with one another, they need to decide whether their vectors are orthogonal or whether they're epsilon far from orthogonal, meaning that the inner product in absolute value is at least epsilon over D. So we show that when D is at least 3, this problem requires D log 1 over epsilon bits of communication. And again, we have some sort of technical restriction on the number of rounds. There's an
That's it. Yeah.